Okay, so in the last video we went through what our expected number of singletons are, and we found that it's 2nu times n divided by n minus 1. And I find that quite amazing that we can write down something this simple. So on the one hand, it's really kind of cool, and this is an example of the power of the coalescence, to take these really complicated things and with a little bit of math, turn them into fairly simple things. But at the same time, this may not be all that useful, right? Because this requires knowing some stuff that we don't know. We don't actually know what n is. We don't actually know what mu is. So while this makes gives us an estimate of the expected number of singletons, it doesn't give us a sense of the expected proportion of singletons. We might instead want to ask, if I've got 100 SNPs in my data set, what fraction of them do I expect will be singletons? And so I thought we'd work out that. And so that means we want the expected proportion of singletons, which is going to be equal to the expected number of singletons times the total number of expected SNPs. So is this hard or is this easy? Well, let's think about it. So in our sample, we can get our total number of SNPs as the number in each of our intervals, right? So what's the number of mutations in this interval? Well, we have n lineages, and then we have each one of them is mutating at rate u, and the expected time, let's do this more formally. So for this interval, so we have now we're back to our old friends, the normal m over c. So m1 here is the number of lineages that we still have left, times mu divided by the rate of coalescence, which is n times n minus 1 over 2 divided by n. Okay, so we can simplify this. This is 2nu over n minus 1. So that's the total number of mutations that we expect to occur here. So the total number of SNPs that we expect to have been generated in this interval. So here, now we have n minus 1 times mu divided by n minus 1, n minus 2 over 2n, which simplifies to 2nu divided by n minus 2. And in fact, if you work it out, you'll see that this one is 2nu divided by n minus 3, and this is 2nu divided by n minus 4. And so in general, our total number of SNPs is going to be, for our ith interval from 1 to n minus 1, that's the number of intervals we have, that is going to be equal to 2nu times 1 divided by n minus I. Right? So n minus 1, n minus 2, n minus 3, all the way to, I think this is n minus 2. No, I think it's right. Right, so it's going to be 2nu times 1/5 plus 1/4 plus 1/3. Sorry, 1/4 plus 1/3 plus 1/2 plus 1 over 1. Okay, so I don't know a simpler way to write this except for in its form here. But in general, this gives us our expected number of SNPs. So let's actually go ahead and work this out. Let's write it down. So that would mean this is 2nu divided times n divided by n minus 1. And this bottom is 2nu times the sum of 1 over n minus 1 and hopefully I didn't make a mistake. sum of 1 over I from I equals 1 to n minus 2. And so in the next video, we'll go through what some of these values are.